my dear friends, welcome to IMS Academy. I hope you people are doing good and you people are working hard for the next year's GATE examination, and in that respect we have been doing this foundation series since past 10 days, and I hope that you people are enjoying the sessions like anything, right? So yesterday we learned the basics of SFD and BMD, and I told you the equation way of drawing the SFD and BMD. And today what we will do, today we are going to learn another technique of drawing SFD BMD, and that is the graphical method. And so you will see that how with the help of graphs we are so easily able to predict the SFD and BMD, but of course it has also got some limitations. So what we will do ultimately, we should be able to draw the SFD BMD in a correct way. So we have to use both the equation way and the graphical method altogether, right? So this is the series that has been running on foundation course on strength of materials, and let me tell you that the sessions that are going on, they are beneficial to every kind of student who wants to have a good foundation in the subject strength of materials. This is our Telegram channel. You can consider it joining. Once you join, you will never miss the important government job notifications, and along with that there will be quizzes and many more. And I'll tell you that these are the course features that are available with us. So there is 800 plus hours of live online class, 34 years of GATE question bank have been provided to you. 2 booklets are there, one for the core subjects and another for the engineering maths aptitude. 12 personalized one-to-one sessions will be provided, and along with that test series and much more will also be there, right? So my dear friends, yesterday we saw that what is a beam, what are the characteristics of a beam, and what is SSB, cantilever, overhanging beam, all these things we saw. Then what is shear force, what is bending moment, what is the purpose of SFD and BMD. Then this was the sign convention that have been used, and in 3-4 steps I have written what are the steps to draw SFD and BMD neatly, and we have seen with the help of examples that how we are how we have to draw SFD and BMD. Now 2 examples I have already taken. This is the third example that we have to draw. This is the third example we have to draw, but before that we will learn the concept of graphical method. Before that we have to learn the concept of graphical method, and for that reason only what I have done, that I have taken some part of this. I've taken some part of this. I have taken a small section of this. I have taken a very small section of this. I have taken a very small section of this. Okay, dx. So this I have taken over here. Okay, so this section I have taken, and this I am analyzing that what is happening over here. Now we have to consider this part. So the distance that, now obviously I am enlarging it, but it is not that much enlarged. So the distance over here is dx. The distance over here is dx. Acha, on left hand section of the beam, I am assuming that shear is acting on the upward direction with a magnitude of V, and if this has to be in equilibrium, see, this is the W weight. This is the W weight that is over here. W distributed load. Now this is the beam. This is the beam. This part is the beam. This part is the beam. So over here on this face, V shear force is applying. So if this have to be in equilibrium, so that if on this part if V is there, so on the opposite part, you know, it will be in the downward direction, the shear force. That means overall it is trying to produce a clockwise, you know, effect on the beam. So if this is V, after some distance obviously it will be different from V, it will not be V. So I am just assuming some change is there, some change in shear force. Shear force is changing, but not that much amount, but small amount it is changing. So for that reason I am assuming it is V plus dV. Similarly on left hand part of the beam I am assuming moment is also there. So on this face the moment, if it is acting in the anti-clockwise direction, so on this face if the entire system has to be in equilibrium, just a minute, so this is V plus dV. If this is the moment m, so on the opposite side, and I am assuming that the moment is m plus Tm. That means I am inducing some change in the moment. So I am purposefully, making it, it is changing by differential quantity, and overall the system have to be in equilibrium. Now these are the forces are there, and if the system is in equilibrium, for the element to be in equilibrium, for the element to be in equilibrium, so obviously the summation of forces in the y direction must be 0. So what are the forces in the y direction? So V minus V plus dV, and this is also acting downward, so minus W, and since it is a distributed load, so you have to multiply by distance, then only it will be the total load. So this is coming out to be dV by dx. If you simplify this, dV by dx is coming out to be minus of W. dV by dx is coming out to be minus of W. So this is one relation that we have got. This is one relation that we are getting. This is one relation that we are getting. Let me name it as equation number 1. And similarly I have to do the moment balance also. Similarly I have to do the moment equilibrium also. So similarly summation of moment, let's say at, I have to take moment at a point, so let's say this is A and this is your B. So I am assuming moment at A is 0, so I have to take the moment of all the forces to be 0. So V is acting, so due to V, no, let's say anti-clockwise I am taking as positive and clockwise I am taking as negative. So due to V no moment is there, but M is also there, M is also there, right? So plus M, okay. Then what are the what are the forces? Now due to V plus dV, so V plus dV into dx, okay. So plus V plus dV, that is the force, the moment due to this shear. Again M plus dm, but it is acting in the opposite direction, that means opposite sense is there. So M plus dm, for writing this I have to put minus sign because it is in the opposite sense. And finally moment due to the distributed loading is there. Again I have to take it as positive because it is in the same sense of M. So W into dx, if I take the moment, so first you have to write W into dx, and you know that the distributed loading acts on the CG of the centroidal area. So this is a rectangular distribution of force. So the centroid will exactly be at the middle. So this is the force into distance. So the midpoint will be dx by 2, and net moment will be equal to 0. So all these things are there. So we have to simplify it. M plus v dx plus dv into dx minus m minus dm plus w into dx whole square by 2. Now dv into dx, this term, and dx into dx, this term, previously originally dx and dv dx are very small terms. So we can neglect it. The product of two small terms is nothing but very negligible. You can neglect this. Again m and m you can neglect it, and what is left? V dx is equal to dm, and finally dm by dx is equal to v. dm by dx is equal to v. dm by dx is equal to v. So this is the second relation that we are getting. This is the second relation that we are getting. This is the second relation that we are getting. And let me name it as equation number 2. So see, these are the two relations which will help you a lot in drawing the SFD BMD, but try to analyze it, what this equation is saying to you. This relation is saying you that the slope of the shear force is equal to the minus of the distributed loading at any point. The slope of the shear force diagram is equal to the value of the distributed loading at any point. And what this relation is saying? This relation is saying that the slope of the BMD diagram, the slope of the bending diagram is equal to the magnitude of the shear force at any point. The slope of the bending moment diagram is equal to the value of the shear force at any point, and the slope of the shear force diagram is equal to the negative of the distributed loading. Now if these two relations you have understood and you have kept in mind, that means it will just ease your things while drawing the diagram. It will just ease up your things like anything. One more thing, my dear friends, while drawing this diagram, while deriving this relation, I have not assumed that there is a point load acting in the section. Have I assumed that there is a point load acting over here? No. So that means this relation is not valid in that case, wherever point load comes into picture. Are you getting or not? This thing you people are able to understand? This thing you people are able to understand? Now let us quickly see the importance of this. Let us quickly see the importance of this with the help of this example. Right, now quickly, this question we have solved yesterday. Now quickly I am going to show you how the relationships are coming into picture. Okay, so quickly if I draw the free body diagram for this cantilever, so this was P, and if you remove the support, here it will be P, and this was the distance L. So moment due to this force was coming at the fixed end, so this force was trying to bend the beam in the clockwise sense. So to resist it, the internal moment will develop over here in the anti-clockwise sense, and its value will be P into L, that is equal to moment. So this was the FBD of this beam. Now if I have to draw the shear force diagram, how will I draw? So if I start from the left, you know that we are always starting from the left only. We are starting from the left only. So there is a point load P. So simply draw upward, pointward. This is the point load and its value is P. Now the relation says that dV by dx is equal to minus W. So the slope of the shear force diagram is equal to the minus of distributed loading. Now tell me one thing. From here you do not know how to go ahead. From here you do not know how to go ahead. So the only thing that will guide you is the slope. Yesterday I have discussed this. And this relationship is saying you about the slope itself. So after this you tell me, okay, dV by dx equal to minus W. Is any distributed loading present over here? Any distributed loading is present? No, it is not present. That means over here in this case W is 0. That means dV by dx will be 0. So slope is 0, and if slope is 0 you move in a constant sense. If slope is 0 you move in this way. Slope is 0, slope is 0, slope is 0, you move in this way. But once you reach here, a point load comes into picture. Once you reach here, the point load comes into picture and it is acting in the downward direction. So you draw by the magnitude of P. So this is your positive shear, and this is your SFD. And I already told you that what is the significance or what is the meaning of positive shear. Positive shear means throughout the beam the shear force is trying to have a clockwise rotation on the beam. It is trying to rotate the beam in the clockwise sense. Now quickly let us try to draw the BMD. So this is the reference line I am drawing. This is the reference line I am drawing. Now see my dear friends, at this point, that means we have to start from the left. At this point there is a hogging bending moment, a bending moment which is trying to create a hogging effect. Sad smiley, sad effect. Sad effect. So sad effect means it is negative. So what is the magnitude? PL. So I will draw in the negative side a magnitude of PL. And just for a moment, my dear friends, we have to do a very quick calculation over here. For example, if you would have started to take the distance from the right hand side, just assume that if I can take x from any side, but just for my convention I take it from the left hand side. That is different thing. But you can take from the right hand side also, that there is no issues. So if you would have taken from the right hand side, the moment at this point would have been 0, because P into x would have been the moment, and x is 0 at the extreme end. So moment at the extreme end will be 0. So the moment at the extreme end I know that it is 0, and this I know. So endpoints I have located, and now the relationship is that the slope of dm by dx, the slope of bending moment, is equal to the value of positive shear. And just see my dear friends, slope will guide you how to move ahead. Slope will guide you how to move ahead. So this is saying me that the slope of the bending moment is equal to the value of the shear force. So for this you refer the shear force diagram. Now my dear friend, tell me one thing. The shear force is constant. The value of the shear force is constant over here, as you can see from SFD. So can I say that the slope of the bending moment diagram will be constant? The value of the shear force is constant, as you can see from here. Constant, same value. So the slope of the bending moment will also be constant. So slope equal to constant. Okay. One more thing, it is positive. It is positive. So positively, constant means straight line. Slope constant means straight line. But you could have moved in this way. you could have moved straight and you could have moved in the downward direction. So which direction I would take? As the value is positive over here, so I have to consider this. Now all this I have explained yesterday, that how this line is positive because it is making acute angle, tan of acute angle is positive. All these things I have discussed yesterday. So out of the three options, end points I know, slope I know, so the only way is you move in this way, and it is negative bending moment. So if you remember, yesterday also we have done the same thing. Clear? So all these things with the help of equations also we can do, and yesterday I have done the same thing. Okay. So yesterday again we have done this question, and again this question we will try to solve with the help of the graphical method. With the help of the graphical method we will try to solve this one. Okay. So so if I draw the support reactions, so exactly at the middle it is P. So I am not determining the support reactions, very easily you can make it out that at the end it will be P by 2 and P by 2, since it is the case of symmetric loading. Due to symmetricity I can very easily say that it is P by 2 and P by 2. Now quickly I have to draw with the help of the techniques that we have learnt. Two relationships we have seen. What are the relationships? That for drawing the SFD, dV by dx is equal to minus W and dm by dx is equal to the value of V. Only these two relationships will help me. So let us try to draw the SFD first. Now this is the reference line. We start from the left. So there is a point load of P by 2. So this is P by 2. This is P by 2. This is P by 2. Now how should I move? How should I move ahead? I can go like this, I can go like this, I can go like this. So see my dear friends, what is the slope of the, what is the slope? Slope is equal to minus W. Is there any distributed loading present over here? No. No. So the slope is 0. So the slope is 0. Slope 0 means the middle line. That means we have to move with respect to, in parallel to x-axis. Slope equal to 0 means we have to move in accordance with x-axis. Okay, moving. After this, suddenly a point load comes, and when the point load comes, just shift it by that much distance. This is P by 2 that I have moved. Again I have to move P by 2, then only it will be P. I have moved. After this, again we have to follow this, that what is the slope over here? The slope is nothing but 0. No distributed loading is there. So I will move in this direction, moving. I am moving, and finally over here when you reach the end, one distributed load, one point load comes which is acting in the upward direction. So you simply pull it by P by 2 distance. So this is the positive shear that we are getting, and this is the negative shear that we are getting, and the significance I have already discussed it yesterday. Again BMD is left, so this is the reference line that I have drawn. Now see my dear friends, quickly we have to think in this way, that if you take the section from the left hand side, so moment will come due to P by 2. So P by 2 into some distance. So exactly at the end, P by 2 into 0, that means 0 moment is there. Exactly at the, if you would have taken distance from the right hand side, so P by 2 into 0, so 0 moment is there. So endpoints we have determined. Now from here, from this point, you could have gone in this way, you could have gone straight, or you could have gone down. So how to determine? This will tell you this relation, this will be given by this relation. So what is the slope? The slope is equal to V. And if you see in the first half of the section, the slope is positive. The slope is constant as well as positive. Constant slope, that means a straight line. Positive, dm by dx is V. V is constant. Let's say V value is 5. So dm by dx is 5. That means it's a straight line and it is positive. So constant and positive, that means we have to, that means this will be the way. Now after this, suddenly what happens, in the second half of the beam, the slope is constant but it is negative. So slope constant, negative. So when it was positive, you are going in this way. When it is negative, you have to go in the downward way. And you know that the end point is 0. So you can connect it very well. So you can clearly see that I am able to at least predict the diagram in a very fast way. But one thing is there, I am not able to tell the magnitude, that for example, what is the magnitude of the maximum bending moment over here. This I was able to tell only by the equation model only. Graphical method is very good for predicting the shape of the SFD BMD, but if we have to know the magnitude, or for example at x equal to 2 meter, what is the bending moment, all these values if I have to know, then the equation model is benefit. So what is the aim? The aim is that we have to be good in both the methods. We have to be equally good, and sometimes the combination of both the methods we will require in order to draw the SFD and BMD. Okay, and now let us come to this part, this question again. Now again this question is there. Again this question comes. So how to draw the SFD and BMD? So we have two methods now. We have two methods. One is the graphical method that we have learned just now, and yesterday was the equation format. So let us see. Let us try to explore that, how to draw this diagram, how to draw the SFD and BMD. But first, my dear friends, we have to draw the reaction supports. That was the first step. So let us now include everything. Okay. So first I have to, this is the, okay. So over here you can see that distributed loading is there, whose value is, intensity is W. So obviously reaction, let's say this is A and let's say this is B. So reaction at A is RA and reaction at B is RB. Okay. Obviously, the distance is L. So obviously I can say that RA will be equal to RB, it will be equal to some value, but okay, let me show you that how to calculate the support reactions. So RA plus RB will be equal to, so what is the value of the net force? That is W into L. Okay, and now one equation, this is first equation, that is the force equilibrium, summation of Fy is equal to 0, and now we have to now we have to do the moment equilibrium, and let's say I am taking at point A. So at point A the net moment will be 0. At point A the net moment is 0. So Ra effect will be 0. So Rb into L. Now the value of, and since this is acting in the opposite sense, so I am writing equal to the value of the in the net magnitude of the force due to distributed will be WL, and it is exactly acting at the centroid. So that means at the middle, so the distance will be L by 2. L by 2 from where? L by 2 from point A. Okay. So L and L gets cancelled out, and Rb will be equal to WL by 2, and if you substitute, this was equation 2, and if you substitute this Rb value over here, so Ra will also be equal to WL by 2. Now this was the case of symmetric loading, so very easily I could have guessed it that Ra and Rb would be equal to WL by 2 and WL by 2. Now suppose we have to draw the okay, let me take it on the next page. Suppose I have to draw the SFD for this. Suppose we have to draw the SFD. This is the SFD. So quickly if I have to draw, now see, Ra is, obviously we always start from the left, convention is there. So Ra is equal to WL by 2. That means one point load in the upward direction, which is WL by 2, is there. Okay. Now my dear friends, see very carefully how to go ahead. This will only be given by this relation, that is dV by dx is equal to minus W. Over here distributed loading is there, and let's say its value will be, let's say 5 kilonewton. So dV by dx equal to minus 5, say, for example, you can assume. So the thing is that this, let's say this is your WL by 2, and from here you could have gone in this way, you could have gone in this way, you could have gone in this way, and dV by dx equal to minus W, which is a constant, minus 5, it's a constant. So it's a straight line, that is fine. But how to go? So dV by dx, if negative, dV by dx, example, if I tell you dV by dx is equal to minus 2, that means the slope is negative. Slope is negative means we have, that is the upper one is the case of positive slope, horizontal line is a case of zero slope, and this is the case of negative slope. That means we have to come down, we have to come down. So I have to come down, I have to come down. Acha, one more thing. At the end there is a upward acting point load. So I can at least sense that there, let's say this line is coming, somewhere it would have been intersecting. I'm just saying somewhere it would have been intersecting this line, and from here I could have just drawn this Rb whose value was WL by 2. So this is one way. So this line is coming, somewhere it would have been intersecting, and I would have drawn this WL by 2. So this is one way of analyzing. I'm just saying, I'm just giving different opinions, that okay, this is, again you will argue that sir it is a symmetric figure. So you just draw exactly at the middle point, so you have drawn unsymmetrically. So I'm just saying that okay, this is one way of thinking. This is just one way of thinking. And another way of thinking is, see, you will appreciate this, that this Ra is already having a value WL by 2. Now after that the distributed loading is acting in the opposite direction, and it is trying to counter, the effect of RA. Think this very carefully. For if you start drawing, so this is RA which is acting, let me draw over here. This is the RA value, and RA is acting at the upward direction. This is RA. Now it is having some value, Now after that, the distributed loading is trying to counter RA. Counter RA means slowly, it is countering. So for example, what is the magnitude of the distributed loading? WL. What is the value of RA? RA is WL by 2. So WL by 2, and now after that it is countering. That means till half of the length, what will be equal to the value of the distributed loading? WL by 2. W into L is the full value. Till half length, it would be W into length kya hai? L by 2. So WL by 2. What is the value of RA? WL by 2. So WL by 2 till half length, shear is also WL by 2. That means net effect will be 0. Net effect will be 0. So why I am trying to say that? Because this is WL by 2. Now it is countering. For example, this is the midpoint. This is the midpoint. Now WL by 2 and the distributed loading is countering, and over here it is coming out as 0. It is till then the effect is balanced. So why did I tell? Because it will help me to guess the diagram even more accurately. And after that, the distributed loading effect increases, because WL by 2 say now the distributed loading effect is more than RA. So it is going down. Now it is more. And finally, someone needs to counter this shear which has been developed. So who counters? Finally, there is RB which is sitting with a value of WL by 2. Till this distance, this is WL by 2, and who is countering? RB is countering in this way. Are you getting or not? So this is one way of analyzing the shear force diagram in a very accurate way. Obviously, I told you that this graphical method will be beneficial for predicting the nature, not for accurately giving you the answers. Okay, so let's say if you have understood this, and obviously I'll tell you that you people need to also think on this. No matter how many examples I give over here, until and unless you people take up an example and start drawing by yourself and see whether the relations are making sense to you, unless and until you do it by yourself, you will never get the confidence. This much I can say. Okay. Now I will try to explain you the BMD. Now I will explain the BMD. Okay. Very neatly, see. If I start from the left hand, only RA, means if I write the bending moment equation, RA and the distributed loading will come into effect. But exactly at the, if I start, so no moment is there. RA into X you would have written, but no distance is there at the beginning, so the beginning moment will be 0. Similarly, if you start from the this hand side, exactly at the tip, force into distance, both the forces W and RB, it is having 0 distance, so moment will be 0. So 0 moment is over here, 0 moment is over here. And what relation I am going to use? I am going to use dm by dx is equal to v. This relation I am going to use. Now my dear friends, see very carefully. From here I could have gone in this way, I could have gone horizontally along the line, and I could have gone in this way. But which way I will go? So see, you know this relation. So this will be given by slope. Where you will go? Case 1, or case 2 straight or case 3 down. So case 1 is signifying positive slope, case 2 is signifying 0 slope, case 3 is signifying negative slope. So see, in the first half of the beam, slope is given by V value, and V value, for V value you have to come in SFD. For V value you have to come in SFD. So let's analyze for the first half of the beam. First half of the beam, that is L by 2. So in the first half, the value of the shear force is positive, as you can see it over here. It is above the reference line, so the value is positive. But my dear friends, the value of positiveness is decreasing. The value of positive magnitude is decreasing. For example, over here if it is 6, so 5, 4, 3, 2, 1, and eventually the value of the SFD is becoming as 0. So one thing is clear, that I should not worry about the negative slope and also the 0 slope case. 0 slope case we should not worry. I will worry only about the first case. I will worry only about the first case. I will worry only about the first case. So slope is positive, but at the center, the slope value is coming out to be 0. So 0 slope means it is somewhat parallel to x-axis. So positive slope, over here it is positive slope. So positive slope means something like this. See, this is a positive slope. If I ask you what is the slope of the bending moment, it is positive. Tan theta, acute angle, positive. Over here if it is 0 slope, that means tan 0 with respect to x-axis, it will become horizontal, complete horizontal it will become. So from here the slope slightly decrease, the slope positive but decreasing. Now see, decreasing, slope decreasing, and finally it goes to 0. Again from here I have reached over here. After that the slope is increasing but in the negative magnitude. That means 0, -1, -2, -3, -4, -5. So slope is increasing but in the negative. Negative means what? Here it is 0 slope and it is increasing 0, now increasing, and finally it will reach the maximum slope at the end, but its value is 0. This thing you people are able to understand? This thing you people are able to understand? I hope this approach is clear to you. I hope this approach is clear to you. If the two relations are clear, that is dV by dx is equal to -w and dm by dx equal to v. If these two relations are clear and your slope concept is clear, then you will have, you will be very comfortable while accurately predicting the SFD and BMD of the curves. Tell me if you are watching, you can tell me that yes sir, we are getting it or not. But one demerit is there. What is the demerit over here? The demerit is that, can you tell what is the maximum value of the bending moment? If I ask you that, okay, you have predicted the diagram SFD BMD neatly, but can you tell the maximum value of this? You will say no. So for that, what we can do, we have to refer the equation format. We have to use the equation format. So let us now neatly do it with the help of equations, that how with the help of equations we can accurately predict the the magnitude of the maximum value. Okay, so this is just for diagram, and now let us okay. So I am now drawing it. So I am not drawing the question, I am straight away focusing on solving now. Okay. So this was the free body diagram. This was your WL by 2. this was your WL by 2, and over here it was the distributed loading with a constant distributed loading with W. So now I am drawing the SFD. So for writing the equation, what was the step? The step was that at any distance x, let's say at the section xx dash, at any distance x, I have to write the equation. So what is the shear force equation at section xx dash? So positive WL by 2, and this is coming downwards. So minus intensity into distance, W into x. And this equation, if I ask you that can you write it over here, so this will, you will write the same equation. If I ask you can you write it over here, you will write the same equation. So this is the equation which is applicable for throughout the beam. Now what I can do? I can find out the values. So let's say at x equal to 0, that is at A, what is the value of the shear force? You just put 0 over here and you will be getting WL by 2. If I ask you that at x equal to L, what is the value? So you will substitute L over here, and if you substitute over here, you will be getting WL by 2 minus WL, that is minus WL by 2. And one more thing, where the shear is becoming, what is the value? First of all, is it becoming 0? Is the shear becoming 0? This you need to, find out. And if it is becoming 0, at what distance it is becoming 0? So this thing for Sx x dash is equal to 0. So where it is becoming 0? So WL by 2 minus WL x is equal to 0. So if you simplify, you will be getting that at x equal to L by 2, it is becoming 0. For shear force to be 0, it is becoming 0 at WL by 2 minus Wx. You simply equate it to 0. So this is becoming 0 at x equal to L by 2. So at both the extreme I know, where it is becoming 0 I know, and what is the slope? What is the slope of this? So d of Sxx by dx, what is the slope? The slope is coming out to be minus W. So slope also I know. So everything I know. I know the slope also. So at xx equal to 0, WL by 2, so this is WL by 2. At L it is minus WL by 2, so minus WL by 2. And exactly at L by 2, that is at the middle point, it is becoming 0, and the slope is minus W. So up, horizontal or down, so down I will go. So down you will go, you will make it 0, and then you will, since it's a constant slope, so you will go in this way. So this was the diagram that we predicted, and very neatly we can say that okay, this is the SFD. Okay. The interpretation I have told you that in the first half the shear is trying to create a clockwise rotation on the beam. In the second half the shear force is trying to create a anti-clockwise rotation on the beam. Okay. And my dear friends, what about the bending moment, BMD? What about the bending moment? So this is WL by 2. This is WL by 2. This is the W distributed load. So if I have to write the equation, so this I will do with at some distance x. At some distance x I will write. So what is the bending moment equation at some distance? Let's say this is the plane xx dash. So at xx dash, what is the bending moment equation? So WL by 2 force, well, the bending moment is coming due to two forces, one due to the point load and one due to the distributed loading. So this point load is creating a sagging effect, that is a smiley effect, so it will be positive. The distributed load is creating a hogging effect or the sad effect, so it will be negative. So WL by 2 into the distance x minus, what is the magnitude of the distributed load till x? It is W into x. And if I have to take the moment at xx dash, what is the centroid for x? Centroid for x is x by 2. So first the magnitude of distributed loading till x, Wx, into distance which is acting at the centroid x by 2 from the section, so x by 2. So WL by 2 into x minus Wx square by 2. Now this is the value of the moment equation, and if you write the moment equation over here or if you write it over here, it will have the same value. So this is the single moment equation that you can find out. Now what I will do, if I have to draw the diagram, if I have to draw the bending moment diagram, so I will find out what is the value at A, that is at extreme left, what is the value at the B, which is the extreme right, at L by 2, that is the middle point, what is the showing and how the slope is there. These all things I will find out. So let us do one by one. So at x equal to 0, what is the value? You substitute 0 and 0, it will become 0. Very good. At x equal to L, because you know x is L, so what is the moment? So I am substituting x equal to L, so WL square by 2 minus, if you substitute L, WL square by 2, and it is becoming 0. So this is 0. So 0 and 0, 0 and 0. Okay. Secondly, what is the value at at x equal to L by 2? This also we can find out. Okay, ठीक है. ठीक है, but we need to know how to go. So for that we have to find the slope. Slope is needed. Slope, without slope you cannot do anything. Okay. So dm by dx. What is the slope? The slope is coming out to be WL by 2 minus Wx. This is the slope. So this equation is saying you clearly that the slope is not constant, it is changing with x. So what is the slope? Let's say this is m. Let's say this is m. Say. So what is the slope value at x equal to 0? So at x equal to 0, if you substitute over here, the slope value is WL by 2. That means it is positive. It is positive slope. Positive slope means its face will be like this. Its face will be like this. Okay. Let me see at the end, that is what is the slope at x equal to L. So at x equal to L you substitute over here. So WL by 2 minus WL, x equal to L. So this is coming out to be minus WL by 2. So at the end the slope is negative. Slope negative means its face will be like this. Its face will be like this. So if it is going like this, if it is entering like this, definitely in the middle somewhere the slope would have been 0. So where the slope is 0? Where the slope is 0? So WL by 2 minus Wx equal to 0. If you find it out, the slope is 0 at L by 2. So exactly at L by 2, exactly at L by 2, exactly at L by 2, the slope is 0. So see, three things we know, and this is nothing but a quadratic equation. If you see this equation, this is nothing but a quadratic equation. That means it is not a straight line, it is a curve. So based on all this data, we can very neatly draw curve. So it is positive, 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 decreasing, decreasing, positive, and it is increasing, negative. So over here the slope is positive, over here the slope is 0, and over here the slope is negative. How it is positive? You take angle tan theta, acute angle positive. Over here tan 0, tan of 0 is 0, and tan of obtuse angle is negative, so slope is negative. Right? And one more thing, yes, what is the maximum value of here? What is the maximum value? So in the bending moment equation, you simply substitute. See, at x equal to L by 2, the slope is 0, and you know that at the stationary point only, the function either gives a maxima or the function either gives a minima. Over here it is giving a maxima. So what is the value? The value will be at x equal to, in the bending moment equation, at x equal to L by 2, you substitute. So WL by 2 into L by 2 minus W by 2, and in x L by 2, so L square by 4. So this is coming out to be WL square by 4 minus WL square by 8, and this will come out to be WL square by 8. This will come out to be WL square by 8. So what is the value? This value is WL square by 8. WL square by 8. So as I was saying that in the previous case, although I was able to predict it very accurately only, the slope, the diagram, but I was not able to tell the maximum or the minimum value. But over here, when I am writing the equations and doing all these things, I can literally predict anything. I can tell that at x equal to L by 4, what is the value of bending moment? At x equal to 2L by 0.6 L, what is the value of the bending moment? All those equations I can tell, because now I have the equation with me, right? So although this is looking a bit clumsy, but if you have followed the lecture neatly, you will be able to figure it out, the things. So my dear friends, this was the second lecture of SFD and BMD, and this is the last lecture of SFD and BMD as well. And what I hope after this lecture, that your concepts and the basics in SFD BMD will be very, very clear, and this logic you apply in any question, and trust me, you will not face that much of a difficulty dealing with SFD BMD questions, right? So I hope you are enjoying the lectures, and in case you are finding it useful, you can drop your valuable, you can like the video, you can share it with your friends, you can, if you have any doubt, you can leave in the comment section as well. And if you are finding it useful, and informative, then you can share it with your friends also who wants to build a very good foundation for the subject SOM, that is the strength of materials, no matter whether they are preparing for GATE or they are preparing for their semester examinations, right? So this is the Telegram channel, you can consider it joining. You will be getting live updates of the government job notifications and daily quizzes. And finally, if you consider joining our online course, so here is the data: 800 live class, 8 hours of lectures, 34 plus years of PYQs, 12 one-to-one sessions, and 130 online and offline tests you will be getting, right? So my dear friends, with this we end the session, and next week I will be taking more 2 sessions in this series that I am we are running. So mostly one will be on bending and another will be on torsion. This is as for the tentative schedule, and if you guys are finding it useful, we can run much more series like this in the future. But as of now, in the current series, we will be having 2 more sessions. So let me remind you, before ending the video, let me remind you what are the chapters that we have already covered: simple stress and strain, stress transformation in very detail, then SFD BMD in very much detail. So what are the important chapters we have already covered in much detail, right? So till then, take care, God bless, stay keep studying, and we'll be meeting next week on Wednesday. So the last 2 lectures will be on Wednesday and Thursday. Next week Wednesday and Thursday. Tomorrow we don't have any lecture. Fine. Bye. Take care. God bless. Jai Hind.